Hello. I'm going to wait a minute or two for people to roll in before I get started. Hello, Jackson. Let's see, how many people do we have in this class? Hello. Hello. Are you actually in Kyoto? I am waiting about 1 more minute, maybe 2 more minutes for the rest of the class to join. I can see there are 10 of you viewing currently, and there are 20 people in the class. It's a long story. Okay. I will ask you in the Zoom room. Hello there. I'm waiting 1 more minute. Oh, here comes someone. All right, I'm going to go ahead and start. Maybe I should. I'm going to go ahead and start. So, first of all, welcome back to our virtual class. I'm teaching a lot of you guys twice because I'm also doing computer science, so it's kind of funny. I've never had that experience before. So, a couple of things. First of all, I would like to remind you to click the button on the Canvas page and submit your daily attendance if you haven't done so already. You get the attendance will be counted as valid 5 minutes before the class starts, all the way to 5 minutes after the class ends. Okay. The second thing I wanted to say is after I'm done with my lesson here, we will migrate over to the Zoom room. I will immediately begin the Zoom room, and I'll admit everyone. And in the Zoom room today, I will show you how to access your daily quiz, and we'll work on it together. So that'll be nice. And I also wanted to let you know that office hours is from 1:30 to 2:30. And if you need to communicate with me in office hours, please go to the same Zoom room, my virtual classroom, and I'll be there. Okay? And I will also be dealing with any technical issues that you guys are having there. So my plan is during the office hours, I will allow guests to share their screen so that you can share what the problem is, and I can help you out a little bit more easily. The live chat, I'm monitoring the live chat, so if you have any questions, type it into the live chat and I will be happy to answer them. Just keep in mind there's about a 20-second delay between I'm seeing you type into the live chat immediately, but when I give my answer, it might be 20 seconds delay. Okay. So I'm going to go ahead and switch to the document cam. So you can take notes on paper if you want to. You can just watch and not take notes. I don't really care. It's a college level class. So you do what you need to do to learn the material most effectively. Okay? So let's get started. Today's lesson is going to be just sort of a mathematical overview of vectors. So that's what today's lesson is about. Okay? And the next time I see you, which will be Thursday of next week, we'll apply vectors to kinematics, essentially. All right? So this is going to be pretty much pure math today. So a vector, basically a vector has a length and it has a direction. So we can draw the vector as an arrow. Okay, so that would be an example of a vector. Let's say that's a vector v. Okay, so that's a picture of a vector. Now notice how this vector goes to the left a certain amount and it goes up a certain amount. So the amount that the vector goes over, that is called the x component of the vector. The amount that the vector goes up is called the y component. Okay? So I'm going to give these numbers. So for this vector, because it goes up, the y component is positive. So we'll say that the y component is maybe 6. And then we'll say that for this vector, the x component is, it goes to the left. So the left is the direction of the negative x-axis. So that's going to have a negative x component of maybe, let's say, -4. So if I was going to write this vector algebraically, I would say v equals -4i plus 6j. So that's the vector in algebraic form. So to indicate a vector, you put an arrow over the top. Okay, that's if I'm writing a vector. If you're writing a vector by hand, you put an arrow over the top to indicate that it's a vector. If you're reading a textbook and the textbook mentions a vector, instead of putting an arrow over the top, the textbook, that letter will be in bold. Okay, so either bold or arrow over the top indicates vector. Okay, and vectors are always going to have an I and a j, and you simply write the x component, the number for the x component, in front of the I, and the number for the y component in front of the j. And I bet you can guess. So this is for two-dimensional vectors, vectors that are in a plane. Okay, it's also possible to have three-dimensional vectors. A three-dimensional vector goes over a certain amount, it goes up a certain amount, and then it goes into the page a certain amount, towards you guys a certain amount. And so if you have something like that, it could have plus a k term, and even more. In special relativity, space-time is four-dimensional, so you have if you have a vector in space-time, it's going to have an I, j, k, and then another. Usually that's called the t component, the time component. All right? So that's a vector. I'm going to have another vector. So let's choose a vector like maybe this. So I'll call that vector W. Get out of here, Potato Master. Come on. You know, I can almost read that, Potato Master, because I used to take Japanese in high school, and I know that the first two, it says like in something, because that's katakana, I think, or hiragana or something. All right. You distracted me, Potato Master. So for this vector, let's say it goes over 1 or so. And let's say this vector goes up 7. All right? So if I wanted to write the vector W, that would be the vector 1i plus 7j. All right? Now, one of the things we can do is we can add together vectors. Okay? So how do we add vectors? Well, what you do is you take the two I components and you add them together. Okay? So -4 plus 1 would be -3. So that's the I component. And then the j component, we take 6 plus 7 is 13. So -3i plus 13j is the sum v plus w. Okay? This operation is called vector addition. We are taking two vectors and we are adding them together. Okay? You cannot. What if I had the vector v and I added 5 to it? Is 5 a vector? I hope you can see that the answer is no, because 5 doesn't have i's and j's and stuff. It's only going to be a vector if it has i's and j's. So this makes no sense whatsoever. This makes me cringe. I'm cringing to see this because it's like combining apples and oranges, okay? We're adding a vector to a thing that is not a vector. It's just a number. So this is a big no-no. All right? Don't ever do that. The other thing I wanted to say is if you have just the vector I, if you don't put any number in front of it, then you assume that the number in front is 1. So this is like 1i. And then because I didn't even put a j, you can assume that the j component is 0. So this is 1i plus 0j. All right? So, and similarly, if I had -j, for example, that would be 0i minus 1j. So the j component is -1. All right? So another thing I wanted to talk about is we can take a vector and we can multiply it by a number. So let's say we had 3 times v. So this is allowed. We have 3 times the vector minus 4i hat plus 6j hat. Okay? And so how you do that is you simply distribute. Okay? So you'd have 3 times -4 plus 3 times 6. So that's going to be -12 I hat plus 18 j hat. Like that. Okay? This operation is called scalar multiplication. So if something is just a number, so scalar is basically another word for just a number. Okay, so a scalar is just a number by itself. A vector is an I and a j with numbers in front of them. Okay, so scalar multiplication is taking a vector and multiplying it by just a number. Okay, so that's one thing. Another thing we can do with vectors. So there's scalar multiplication. There's vector addition. The other thing we can do is we can get the magnitude of the vector. And the magnitude is just equal to the Pythagorean theorem. Okay, so you do the Pythagorean theorem on your vector. And the magnitude would be denoted by, so I'll put the vector and I'll put vertical bars around it. So kind of like absolute value. Okay. And so if I wanted to find the magnitude of the vector v, well, I do the Pythagorean theorem on this triangle here. Okay, so that would be, -4 quantity squared plus 6 quantity squared. Keep in mind that when you square the negative, it goes away. And so we would get 16 plus 36, which is what, 52? I think so, yeah. So the magnitude of that is square root of 52. Okay. Yeah. And you would convert that to a decimal number. All right. So all this stuff that I've been talking about, this is algebraic, that we would call this algebraic manipulation of vectors, because algebraic means with numbers and variables and doing things with equations. But we can also think of vectors in terms of pictures. So I want to talk to you, how do we understand vectors in terms of pictures? All right. So I'm just going to talk about pictures of vectors. So let's suppose that I have my two vectors. Let me remember what they look like. So V kind of looks like this, and W kind of looks like this. So how do I get, what is the vector that corresponds to the sum of the two vectors? Okay, the vector addition. What you want to do is you want to make a parallel. You want to first of all put the vectors tail to tail. Okay, so I've taken the two vectors and put them tail to tail. And then I'm going to draw a parallelogram out of those vectors. Like that. And then the arrow that goes across the parallelogram is the sum, V plus W. So that's the meaning of, and then once we draw it, we can then move it someplace else. So there's V plus W, approximately. So that's the picture of how we add vectors, okay? That's what it means in terms of pictures. Let's talk about what does scalar multiplication mean in terms of vectors. So if you scalar multiply, let's say we have a vector A. We have a vector A. Here's the vector A. If we were to multiply the vector by, let's say, 2, the vector 2a would be the vector that points in the same direction but is twice as long. So it's going to be something like that. Okay. Similarly, if we did a over 2, that's, you can also do scalar division, right? So that would be a vector with half the length. okay? So that would be this vector, for example. If you multiply a vector by a negative number, that reverses its direction. So if you had the vector minus a, in terms of pictures, that's going to be the vector in the reverse direction. So it's going to be the anti-parallel vector to a. All right? So this is the meaning of scalar multiplication in terms of pictures. Okay? And then getting the magnitude is simply the length of the arrow. Okay? So I have a question for you, which is, what would be the magnitude of the vector v divided by its magnitude? What would be the length of that vector, the magnitude of that vector? I'm going to wait for someone to type it in to the live chat. Yes, the length is 1. Excellent. So why is the length 1? That's because, well, let's say the vector had, let's say v had a length of 25. You're taking 25 and you're dividing it by its length, so it's going to be 25 times shorter. So its new length is going to be 25 over 25, which is 1. Okay? So whenever you take a vector and you divide it by its length, you make its length 1. Okay? So this is called a unit vector. Okay? And the shorthand for a unit vector is to use the same symbol, but put a caret over the top. Instead of an arrow, you put a caret, and that means take the vector v and make it a unit vector. Okay? So these are, unit vectors are very useful in physics. Okay? All right. So we're going to go to CHL 9.3, period 7, 2. Okay. So now we're going to talk about some funkier stuff. So we're going to talk about something called the dot product. And the dot product takes two vectors, and so that's the input. The input is two vectors. The output, the result of it, is a scalar. So remember, a scalar is another word for just a number. Okay? So how do we get the dot product? Well, let's say we have two vectors, v and w. The dot product is denoted by v dot w. Okay? And it's going to be equal to the x component of v times the x component of w plus the y component of v times the y component of w. Okay, so we multiply the x components, we multiply the y components, we add those two together. Okay, and that's how we get the dot product. So let's do that. So here's our piece of paper with v and w. Okay, so what's the x component of v is minus 4. So we have minus 4 times the x component of w, which is 1, plus the y component of v, which is 6, times the y component of w, which is 7. Okay? So that's going to be minus 4 plus 42 equals 38. So that's the dot product of those two. Notice how when I get the components of the vector, so that the x component of v is not minus 4i. It's just minus 4. So the component is just the number that's in front of I, or the number that's in front of j. All right? The other thing I want to talk about is if you had 3 dimensions, if we were talking about a vector in 3 dimensions or 4 dimensions, you would just add an additional term. It would be z component of v times z component of w. Okay, so this pattern continues depending on how many vectors there are. And in fact, if you're in my computer science class, we're going to eventually be writing some. We're going to write a vector class, and I'll have one of the methods in the vector class, so I'll have you do dot product and cross product and all that stuff. All right. So this is one way. This is how you algebraically compute the dot product. But what does it mean? What does the dot product mean? Well, it is the. It turns out, I'm not going to prove this, but if you come to my office hours at 1:30 in the Zoom room, I can prove this to you if you like. And it turns out that the dot product is equal to the magnitude of the first vector times the magnitude of the second vector times the cosine of the angle between the two vectors. All right? So, if these are the two vectors, then when I say the angle between them, I mean that. So that's called the dot product. All right? So if we don't have the dot, then that would be scalar multiplication. So it doesn't make sense to write VW like that because there's no dot in between. So that's a no. It doesn't make sense to say 5 dot v because that's implying dot product, and a dot product takes 2 vectors to a scalar. So that doesn't really make sense. But you could say 5v because that's saying scalar multiplication. All right. And the last thing I want to talk about for today is something called the cross product. And I'm going to teach the cross product in a way that it could be totally different from your math class. Okay. I'm going to teach it in a weird way. Let's think about the alphabet. I, J, K. That's the order of those letters in the alphabet, right? But we're going to think about the alphabet cyclically. So what happens after K? Well, normally what would happen after K is L. But because we're only dealing with I, J, and K, once we get to the last one, we go back to the beginning. Okay, so it's circular. So I, J, K, and what comes after K is I. All right. So let's say I had J, K, I. That's in the correct order. Okay, because what comes after I is J. But see how I'm at the end of the line here? So once I get to the end of the line, I go back to the beginning, and I find J. J does in fact come after I. And then K. K comes after J. And then, so that's in the correct order. Okay. Similarly, K-I-J is in the correct order. Okay. Because it's I, then J. And then once I run out of room, I go back to the beginning, and I find K. So it's I-J-K. So all of these are in the correct order. All right? But if I had KJI, that's in the reverse order. Okay? Because what comes after I here? It is not J, because what comes after I is I go back to the beginning and I find K. So that's reverse order. Similarly, that's reverse order, and IKJ is also in reverse order. So these are all in the reverse order. All right? So how does the cross product work? Well, the cross product takes two vectors and it spits out another vector. Okay? So what if I have the two vectors, I and j? What does I cross j equal to? Well, is I cross j in the correct order? And the answer is yes, because j comes after I. So that's going to be equal to k. So anytime you have things in the correct order, then it's going to equal a positive sign. All right? But if I go j cross I, that's in the reverse order. See how ji is the reverse order. So in that case, the answer is going to be minus k. If it's in the reverse order, it has a minus sign in front. All right? So your cross products are always going to have all three of them, I, j, and k. And whether there's a plus sign or a minus sign depends on whether it's in the correct order or in the reverse order. So the cross product is sort of it's a little bit different from regular multiplication, because if we think about regular multiplication, 4 times 5 is equal to 5 times 4. Okay? It's commutative. That's the commutative property of multiplication. But cross products, if you reverse the order, you get a minus sign. All right? And if you must know the fancy term for something that gets a minus sign when you reverse them, we would say it's anti-commutative. Okay. So what would be j cross k? What would that be equal to? I'll wait for you guys to type it in. It's equal to I, right? Because k does, in fact, come after j. All right, so that's the correct order, so it's going to be a plus sign. All right? If you have the same twice, so for example, I cross I, then it's just automatically equal to 0. All right? So you have to have all three in order to have a cross product that is not 0. So let's do an example. What if I had the vector 2i plus 3j cross let's say 2j plus 5k. So how do I do that cross product? Basically, all you're going to do is you're going to FOIL it. You're going to FOIL it, but the thing you have to be careful of, Jacob, I'm not sure I understand your question. I'll answer it during office hours if you remember it. Okay, so what we want to do is we want to FOIL this, but we want to make sure we keep things in order. The reason that we have to keep things in order is because of this anti-commutative property of the cross product, so we can't flip them. So FOILing, the first term would be this one. So that's going to be 2 times 2 times I cross j. All right, so notice how I'm keeping the I and the j in the correct order, because the I is on the left side, the J is on the right side. Okay. Then I do the outside term. The outside term is going to be 2 times 5 times, and then again, I have to keep these in the correct order. Okay. So it's going to be times I cross J plus, and then I do the inside term, which would be that. So that'll be 3 times 2 times J cross J. And then the last term is this one. And that one is going to be 3 times 5 times J cross K. All right. So now we just got to simplify it. Well, what's I cross J? I already have that right here. It's plus K. All right, so I have 4K. I cross K. Who can tell me what I cross K is? I'll wait. So it's going to be 10 times whatever that is. J cross J is going to be 0. And then I have plus 15. So you got to be careful here. It's going to be something times J because the cross product is always going to be equal to the one that's left out. But IK is the reverse order, so it's going to have a minus sign. So we'll get, this will be minus J. Very good. And then this J cross K is I. So this would be, if I wanted to write it kind of in a more standard way, I would put 15I minus 10J plus 4K. All right. What does the cross product mean? What is the meaning of A cross B? Well, the magnitude of A cross B is equal to the magnitude of A cross B is going to be equal to the magnitude of A times the magnitude of B times the sine of the angle between the two vectors. So see how the cross product is pretty closely related to the dot product, right? Because the dot product had a cosine and the cross product has a sine. So you switch the trig function, and the other difference is, of course, that the cross product is going to give you a vector. So I can prove this formula for you as well. I can prove that formula for you as well during office hours, if you like. I hope someone will ask me. I love proving math formulas. All right, so that's my lesson for today. So I'm going to end this stream, and then I will see you guys in the Zoom room in about 1 minute. Okay? So that's all for now. Bye.